Welcome to The Explainer. Today, we're going deep. I mean, literally deep. We're going to explore the incredible technology used to test oil and gas reservoirs that are buried miles beneath our feet. It's a super high-stakes process, and it's absolutely critical for the energy industry.
So let's just jump right in. I want you to imagine this. You've spent a fortune, millions of dollars, to drill a well, but you don't really know for sure what's down there. How much pressure is it under? What kind of fluid will you actually find? Is this thing even going to make money? That is the core challenge, and the solution they came up with is nothing short of ingenious.
And that solution? It's a process called drill stem testing, or DST for short. Honestly, the best way to think about it is like a temporary grand opening for a brand new well. It lets engineers get a sneak peek of its potential.
At the end of the day, DST is all about gathering intel. Before a company goes all in on the massive cost of building a full-scale production facility, this test gives them the vital signs, the reservoir pressure, the fluid properties. It's how you de-risk a colossal investment. It lets you know if you've hit the jackpot before you bet the farm.
Okay, so how does this whole thing actually work? Let's get into the nitty-gritty and take a look at the incredible hardware that could send miles down into the earth to pull off this high-stakes test.
Now this is where the physics get really wild. The DST tool has to safely manage this three-way tug-of-war between competing forces. You've got the hydrostatic pressure. That's the weight of all the fluid in the well pushing down. Then you've got the raw formation pressure from the reservoir trying to burst out. And finally, there's the cushion pressure, which the engineers use to control the whole test. It is an incredibly delicate balancing act.
And this is the toolkit that has to manage all of that. You've got these really precise instruments, like the packer, which is basically a super high-tech cork that seals everything off, and the test valve, which acts as the main tap. But you've also got these brute force safety tools, like the hydraulic jar, literally an emergency hammer, and the safety joint, which is your last-ditch, get-out-of-jail-free card if things go really wrong. So the whole thing is designed for both success and survival.
So pretty early on, engineers come to this major fork in the road. They have to make a huge decision that's going to dramatically affect the cost, the speed, and the safety of the entire test. What type of DST are they going to perform?
And this slide really gets to the heart of the trade-off they're facing. On one hand, you've got open hole testing. It's fast, it's cheaper, because that packer seals right up against the raw rock. But what's the risk? Well, if that rock is unstable, your very expensive tool string can get stuck for good. And that's exactly why cased hole testing is the go-to for high-risk or offshore wells. You run the test inside a protective steel casing. It's way safer, but yeah, it's also more expensive and takes a lot more time.
But here's the thing. For the longest time, the traditional way of doing those cased hole tests, the supposedly safer option, it actually carried this significant hidden danger that had everything to do with how the tools were operated.
The problem was just mechanical. It was all about brute force. To get those valves miles down in the earth to either open or close, operators up on the surface had to apply massive amounts of pressure down the well, basically using the fluid in the pipe like a giant lever.
And I'm not talking about a little push. We're talking about huge, huge forces. Pressures could get as high as 3,000 pounds per square inch. That is just an enormous amount of stress to put on the well structure, both that outer steel casing and the inner tubing.
Yeah, pushing the equipment that hard was basically like trying to flip a light switch with a sledgehammer. It created these really serious risks of catastrophic failure, like bursting the casing or just collapsing the tubing. It also meant you couldn't run very complex tests. This whole brute force method just wasn't cutting it in an environment that needed precision, and it pushed engineers to find a better way.
So, this huge problem, it forced them to get creative, and it led to an innovation that completely changed the game, marking this big shift away from raw mechanical force to a sophisticated, a smart system.
And that solution is called the Intelligent Remote Implementation System, or IRIS. Let me tell you, this thing operates less like a sledgehammer and more like a remote control. It's all about using brains instead of brawn.
The genius here is just how elegant the design is. Instead of blasting 3,000 psi from the surface, operators send a quiet, low-pressure, coded signal down the well. A little microprocessor on the tool recognizes that unique signal, uses its onboard battery power, and tells the tool to harness the well's own existing pressure to do the heavy lifting of opening and closing the valves.
And wow, the benefits were a total game changer right away. Safety went through the roof because you're not stressing the well anymore. It let them run an unlimited number of really complex test sequences with pinpoint precision. And because you got rid of things like high-pressure nitrogen chambers, the tools themselves actually became simpler and way more reliable.
This quote just nails it, doesn't it? Drill stem testing evolved from this process of just sheer mechanical force into a smart, data-driven science. And that made energy exploration a whole lot safer and far more precise.
And this whole evolution just leaves you wondering, right? As the search for energy keeps pushing us into deeper waters and more extreme environments, what's the next big idea going to be? What's the next smart solution that's going to unlock the Earth's energy from miles beneath our feet?